Now that we've introduced series circuits and parallel circuits, we're now going to be looking at circuits that are called combinations, meaning that they have some elements that are in series and some elements that are in parallel. So some resistors that are in series with another and some that are in parallel. I want to just recall that you remember the mnemonic device that we said that would be very useful during this unit, Vir Sakapakara. You can see that it's typed out nicely here for you to refer to it as we go ahead and analyze this circuit. Just like in the other two circuits, we're going to begin by labeling the circuit based on the information provided in the verb table. So we have 60 volts total, so we're going to indicate that. Again, the longer side is positive, the shorter side is negative. And the zigzags still indicate resistors, so we have a 12 ohm resistor and a 24 ohm resistor 2 and a 12 ohm resistor 3. So why is this called a combination circuit? Well, let's take a look as though we were the current flowing through the circuit. So you come out of the power supply. Do you have to go through R1? You do. There is no way you can get from the positive end of the power supply to the negative end of the power supply without going through R1. After coming out of R1, you arrive at a junction. At that point, you have a choice. You either go through R2 or you continue and you go through R3. Recall that anytime there is choice, we know those elements are in parallel. So because the current has a choice between going through R2 or R3, we know that resistor 2 and resistor 3 are in parallel with each other. So our goal with the combination circuit is to simplify it to be a series circuit. And then we're going to work backwards to figure out the current or the voltage in each piece. So, as we've already pointed out, resistor 2 and resistor 3 are in parallel. So what we're going to do is cover them up and pretend they are one resistor. What I'm going to do is I'm going to draw a box around R1 and R2. And the first thing that I'm going to do is I'm going to figure out what is the equivalent resistance of that blue box that I've just drawn. Now recall that it is covering up two resistors that are in parallel. So what is the rule for resistors in parallel? Well, the rule for resistors in parallel is that reciprocals add. In your calculator, you're going to hit 24, hit the x to the negative 1 button, plus 12, hit the x to the negative 1 button, and then hit the x to the negative 1 button one more time, and you're going to find that the equivalent resistance of this blue box that we have just created is 8 ohms, because that is the combined resistance of a 24 ohm resistor and a 12 ohm resistor in parallel. So, you may recall a moment ago I said it is our goal to reduce any combination circuit into a series circuit. So let's recall what we just did, or summarize what we just did. I'm going to sketch the circuit as simplified. So we had our 60 volts power supply. We had R1, which was 12 ohms. And now we have this second resistor, which is a combination of R2 and R3. And we know that that resistor, which is essentially the blue box, So we'll put RBB for blue box as an equivalent resistance for 8 ohms, of 8 ohms. So now let's just look at this drawing that I've done over here. Well, as you can see, does the current coming out of the power supply have to go through resistor 1? It does. Does it have to go through the blue box? It does. And then it's back to the negative side of the power supply. Was there any choice at any point in this circuit? No, there was not. You had to go through R1, you had to go through the blue box. A circuit where there is no choice is a series circuit. So in order to find the total resistance of this circuit, because we have now reduced it to a series circuit, we must follow the rules for a series circuit. And the rules for resistors in series is that they add. So the equivalent resistance of this entire circuit is going to be 12 plus 8, or 20 ohms. And I'm going to fill that in the verb table below. So now that we've found our total resistance, the next step would be to find our total current. So we're going to take our total voltage and divide by our total resistance and find our total current. And our total current is 3 amperes. So we know that all 3 amps will go now to our drawing. 3 amps comes out of the power supply. Do all 3 amps have to go through R1? They do. So the current in R1 is going to be 3 amps. Do all 3 amps have to go through our blue box? They do. So the current in our blue box is 3 amps. Now, notice I'm going to put that in where our blue box is as 3 amps. So let's make a clarification. Do all 3 amps have to go through R2? They do not. Do all 3 amps have to go through a resistor 3? They do not. But a total of 3 amps must flow between resistor 2 or resistor 3, which we have combined to be that single blue box resistor. Anytime you make a box, you want to indicate what kind of circuit it was covering up, because that's going to help you with your rules. So I've covered up R2 and R3 because they're in parallel. So I like to put a P in the box so I can remember what I was combining. And here's the reason. As we go back to try and figure everything else out, we need to know what's constant in that type of circuit. Okay? So, as you can see, we found the resistance and the current. So if I have 3 amps of current, 8 ohms of resistance, I know I have a total voltage of 24 volts. Now that blue box was covering up what kind of circuit? Well, the blue box was covering up a parallel circuit. So what's constant in a parallel circuit? Voltage. That means that voltage, 24 volts, is constant for everything that the blue box was covering up. And what was the blue box covering up? Well, it was covering up resistor 2 and resistor 3. So I know the resistor 2 should get 24 volts, and I know the resistor 3 should get 24 volts. I'm going to go ahead and fill that in on our verb table right now. So recall that the verb table is laid out such that it begins with Ohm's law. So let's go ahead and figure out our total voltage. I have 3 amps times 12 ohms for a total of 36 volts in resistor 1. In resistor 2, I have 24 volts and 24 ohms, which divides to give me 1 ampere. In R3, I have 24 volts divided by the 12 ohms to give me 2 amperes. Now you'll notice that unlike in the series circuit or the parallel circuit, it won't add up nicely anymore. But it still does make sense, and let's talk about why. So first, let's look at the currents. So let's look in particular at the junction right around that letter P that I drew earlier. So we have the 3 amps coming out of resistor 1. We have 1 amp going through resistor 2, and we have 2 amps going through resistor 3. So you can see that this junction obeys something called the junction rule. The current in is equal to the current out. So I have 3 amps going into this purple dot, and I have 3 amps coming out of the purple dot, because I have 3 going in and 1 plus 2 going out. Now you might remember that in a parallel circuit, current adds. So what is 1 amp plus 2 amps? Well, that adds to our total, which was 3 amps. So let's talk now about the voltage not adding, like it did in, say, a series circuit. So first, let's mark on our picture here how many volts do we drop in resistor 1, and that was 36 volts. Now, voltage still does add to the total, and let me show you why. Let's say we take this path out of the power supply. We go through R1, we go through R2, and we come back to the power supply. How much voltage did we drop? When we go through R1, we drop 36 volts. And then in this case, we went through R2, so we dropped 24 volts. And you can see that 36 plus 24 adds to 60. So in fact, in one path, we do still add to the total voltage across the power supply. Now, what if we didn't take that path? What if we had gone through resistor 1, through resistor 2, through resistor 3, and back to the power supply? Well, we would have lost 36 volts in resistor 1 and 24 volts across resistor 3, still adding to the 60 volts. So whether you took the orange path or that purple path, you should still add to 60 volts. And as you can see, we do. The rest of the verb table is going to fill out pretty similarly to the series and parallel circuits that we did before. So we're going to go through and we're going to multiply our power. So when we multiply, we do the 36 volts in resistor 1 times the 3 amps in resistor 1 for a total of 108. We do the 24 volts in resistor 2 times the 1 amp for 24 watts in resistor 2. And the 24 volts times the 2 amps in resistor 3 to get 48 watts. So we need to add it all up. So 108 plus 24 plus 48 is going to add to 180 watts. Now we need to make sure that we multiply to get to the same thing. So my current total was 3 amps. Times my voltage total, 60 volts, gives me 180. And you can see we multiply our totals, and we get the same thing as when we add the power in each resistor. So in fact, our power check again works out here, indicating that we have done this first combination circuit correctly. So let's summarize the steps of analyzing a combination circuit. First, we had to combine resistor 2 and resistor 3 because they were in parallel, and treat them as a single resistor. We found that the equivalent resistance of R2 and R3 combined was 8 ohms. We found that combined resistor was in series with R1, which had a resistance of 12 ohms. And therefore we found a total resistance of 12 plus 8, which was 20 ohms. That allowed us to find the total current, and we were able to work through the circuit. Let us try another example. Let's turn the page and take a look at the next combination circuit. So, in this case, we have 90 volts on our power supply. Resistor 1 is 4 ohms. Resistor 2 is 18 ohms. Resistor 3 is 9 ohms. And resistor 4 is 5 ohms. So, as you can see, if you were the current, you come out of the power supply. Do you have to go through R1? You do. Do you have to go through R2? You don't, because you could go through R2 or R3. Do you have to go through R4? You do, because even if you went through R2, you'd have to go through R4, or if you went through R3, you would have to go through R4. So right away, we can isolate R2 and R3 as being in parallel. So again, I'm going to draw that box around R2 and R3, and we're going to identify their properties. So I drew a box around them because they are in parallel. So I put a P in the box so I know that it is a parallel circuit that I am covering up, or at least a parallel element. Voltage, current, and resistance. So let's go ahead and use your calculator to figure out the equivalent resistance of an 18 ohm and a 9 ohm resistor in parallel. And again, I recommend using the inverse key, and I believe you are going to get 6 ohms. So I don't always sketch the circuit again, but because this is only the second example, I do want to emphasize what we're doing. So we had our power supply, we have R1, we have our blue box, R4 is still there, can't combine that with anything, and our power supply. So we know R1 was 4 ohms, our blue box was 6 ohms, and R4 was going to be 5 ohms. And we have 90 volts total. So you can see in purple here that I've simplified this to be a series circuit. So we're going to follow the rules for series. Well, if you look at your Vieira-Sacca-Picaro chart, you can see that resistors in series add. So 4 plus 6 plus 5 is going to give you 15 ohms of total resistance. So this circuit has 15 ohms of total resistance. Now that you have your total resistance, you can go ahead and use your calculator to find your total current. And what you're going to do is you're going to take 90 volts, which is the total that's given, divided by the 15 ohms of total resistance, and you're going to get a total current then of 6 amps. So now let's follow that 6 amps through our circuit. So it comes out of the power supply, 6 amps. Do all 6 amps have to go through R1? They do. So under current for R1, we're going to put 6 amps. After coming out of R1, do all 6 amps have to go through R2? They don't, because you could split and go through R2 or R3. Do all 6 amps have to go through that blue box? They do. There is no way for the current to avoid that blue box. So for I in the blue box, I'm going to put 6 amps. When we come out of the blue box, do all 6 amps have to go through resistor 4? They do. So the current in resistor 4 is going to be 6 amps. So recall, the blue box was covering up what kind of circuit? And that's why I told you to always put the letter, whether S for series or P for parallel. In this case, we've covered up R2 and R3, which were in parallel. So that's going to help us here. So in the blue box, we know the current is 6, the resistance is 6, so I know my voltage is 36. Now, because this is a parallel circuit, voltage is constant. That is the rule for resistors in parallel. Voltage is constant. That means that the 36 volts applies to resistor 3 and resistor 2. So I can put 36 volts across resistor 2 and 36 volts across resistor 3. So I'm going to go ahead and fill that in the chart. So you can see that we have either something in voltage or current for every resistor in this circuit. So what is my voltage for resistor 1? Well, it's going to be 6 times 4, 24 volts. What is my current for R2 going to be? Well, it's going to be 36 divided by 18, which is 2 amps. What's my current in R3 going to be? It's going to be 36 divided by 9, which is going to be 4 amps. And R4 is going to be the 6 amps times the 5 ohms, which is going to be 30 volts. Again, you can take a look now. No matter which path we pick, we should add up to 90. So if we go through resistor 1, we drop 24 volts. Resistor 2 is 36, and resistor 4 is 30. So what do we get when we add 24 plus 36 plus 30? We get 90. If we didn't take that path and instead took a different path, going through R1, R3, and R4 back to the power supply, you'll see that we still have 24 plus 36 plus 30, which will again add to 90. So no matter which path you pick in a combination circuit, it will still add to your total voltage. So no matter what path you take, you are going to use all 90 volts. You can see that our current still adds. If you look at that junction by the P, so you can see that at our junction, we had 6 amps coming into the junction. We had 2 amps go through resistor 2, and we had 4 amps go through resistor 3. And again, what's the rule for current in a parallel circuit is that it adds. And 2 amps plus 4 amps gives you the 6 amps. 2 amps plus 4 amps is going to give you the 6 amps. So we're doing this correctly, but let's just go ahead and do the power check to be sure. And recall P is equal to IV. So go ahead and fill that out. So as you can see, I have now filled out the power column. And when I add them up, I get a total of 540 watts. And recall we have our power check. Power total equals current total times voltage total, which is going to be 6 amps times 90 volts, which is also going to give me 540 watts. So you can see that we have our power check. Now remember, the key to combination circuits is to combine resistors until you have a series circuit. And once you have that series circuit, you can find the total resistance, and you can work through and find the voltage or the current in each individual resistor within that circuit. Now that we have done these 2 practice combination circuits, why don't you go ahead and do the third one on your own using the strategies that we have gone over in the first 2.